Yes.
Okay, all right. So I have the privilege of introducing Professor Ali Baklouti today um, as a speaker of this long-going seminar. And Dr. Baklouti is a full professor of math at the University of Sfax in Tunisia. He earned his PhD some years ago from the University of Metz. He served as vice president of the University of Sfax for many years and held the position of the president of the Tunisian Math Society for 2 consecutive terms. His influence has been great on the mathematics in Tunisia. He has co-founded the Tunisian Journal of Math. He's founded the Tunisian Journal of Math and is co-editing it with Ahmed Abbas. Since January 2012, he has been the deputy director of the Mediterranean Institute of the Mathematical Sciences, MEMS, and he was elected in 2016 as a permanent member of the Tunisian Academy of Science and Arts in Tunisia. He is currently a senior expert in research and education at the Erasmus office in Tunisia, I believe, in collaboration with the European Commission. He has received numerous prestigious prizes, including the in 2022, the IMU PACOM medal, which is the highest award in Africa for mathematics. And he has received the Royal Society Prize of the British Academy last year. And I was, again, very privileged to be present in London when this award was given to Ali. He's also gotten the Order of Merit of Education and Teaching by the President of the Republic of Tunisia. So as you can see, he has an unbelievable CV. He has worked on conjectures in deformation theory. He has even his own conjecture there. He made breakthroughs in representation theory. He solved many long-standing open problems. And his contributions has given us deeper insights into many the structure of Lie groups and applications. So without ado delay, I'm very happy and honored to introduce Ali to give a talk. So his talk today is Deformations through Symmetry, Bridges to Life, Sciences and Beyond. Sali.
Thank you very much, Sadak, for this introduction. Thank you, Sirafiq, for this kind of introduction. I'm very pleased to talk today within this group, Al-Khwarizmi Applied Mathematics Webinars. It is a good pleasure for me and for all Tunisian, I think, scientists to introduce in seminar like that, especially people from our laboratory at the University of Sfax. And as Sadak said, today I will talk about some problems related to deformations through the Lie groups, through symmetry groups. And I will give, while I'm not very specialist in that, some bridges to life science and beyond. So let me start slowly. So the first thing is the following. If you ask any artificial intelligence operator, what is the research profile of Ali Baklouti? So the best one I found is this one. It believes that I'm working on representation theory, harmonic analysis, non-commutative harmonic analysis, deformation theory, and discontinuous groups. I think this is a very kind and very nice figure how artificial intelligence can draw a profile of Ali Baklouti. And let me explain a little bit then. So my primary research interest lies in the intersection of algebra and analysis, and this is related actually to the representation theory of solvable Lie groups, non-commutative harmonic analysis, the orbit methods, which is a powerful framework introduced by Kirillov in 1962. And the second part, which is my second area of research, though this is geometry, with emphasis on deformation theory of discontinuous groups, with deep connections with topology, and the rich framework for rigidity and stability of geometric structures. I will speak a little bit and I will explain, because this is a subject which are supposed to be fundamental in their nature, but I will explain how these subjects have their impact on many life sciences. Of course, I would like to thank all the present here in this webinar, especially my students and my collaborators. I would like to thank them very much. Okay, so having this introduction, so the challenge lies in the intersection of analysis, geometry, and algebra. And they continue to inspire a wide array of mathematical investigations. And for nearly 3 decades, my research has been devoted to exploring and resolving a number of long-standing and fundamental problems within this context. Of course, the aim today is not to explain mathematical long-standing problem, because we cannot explain that in 1 hour, but at least give the origin and the circumstances under which I have been and I was interested to such problems. So this related to this plan, to this scheme today. Now, first, I would like to explain you what is the Lie theory, and then what is the impact of Lie theory on life sciences, and the necessity to go from symmetry groups to homogeneous spaces. This is also fundamentals. And I would explain then the deformation theory and some outcomes. And finally, I will explain that this kind of analysis algebra and this kind of analysis only groups entails a deep impact on the so-called non-commutative harmonic analysis related to representation theory. So going from classical harmonic analysis to non-classical one to non-commutative one needs a deep arsenal, a big background on representation theory on these kind of groups. This is what I'm going in whole to explain with some applications and so on. So first, I will explain what is Lie theory. So a Norwegian mathematician named Sophus Lie was looking at differential equations of this form, and he wanted to solve them with a single unifying theory using continuous symmetry. But why using continuous symmetry? Because he was inspired by an earlier mathematician, Évariste Galois, a French mathematician, who was studying polynomial equation, as you know, and equation in the following form. For instance, if you look at this polynomial x to the n plus plus plus, then when n equal 2, you have only 2 solutions, and you need, so Galois explained how discrete symmetries can give a whole operation, a whole process to solve many difficult kind of polynomial equations. Of course, the idea of Lie is to find a parallel way done by Galois in order to solve in whole these differential equations. But at least what we can do now is that he fails to do that. And Lie himself says that I failed to introduce a general formalism in order to solve all these differential equations. But in the case of Galois, so discrete symmetry in the sense that there are finitely many roots of a polynomial, which is actually the setting of the permutation of the roots, which is in some sense easier. But Lie wanted to replicate the success of this Galois theory and made the analogy between the differential and polynomial equation. And as I said, it was a little bit fairer, but behind that, there was, so Lee gave very, very nice ideas about these Lie groups and Lie algebras and so on, which are now potential mathematical issue in order to solve a lot of problems which cannot be solved with the classical analysis and classical algebra. So the symmetry associated with differential equation could be continuous, of course. That's because for differential equation, the situation is completely different from the solution of a polynomial equation. So in general, there is a continuous family of solution, and it is only when you specify the initial condition that you have a single one. Which is quite important is that in the theory of Galois, so you have a finite root, and it is quite easy to establish some groups in order to make the permutation of the root. But in this case of differential equation, sometimes don't see, so the figure here on the screen, so you have a continuous axe of symmetry. You have a whole axe of symmetry. So just you fix the first point of the differential equation, and then you get the infinite set of solutions behind. Lie, and so the idea of Lie is to introduce this kind of continuous symmetry. But what does it mean, continuous symmetry in general? So what I draw on the screen is just an example. So for a whole set, for a big set, for a major set of differential equation, you have some symmetries, which are continuous group of symmetries, which is here just the real line. But in general, it is more complicated. So in order to explain that, we need a concept, an easy concept. It is the concept of group. What is group? A group in general, it is a set when we can multiply. Just a set when we have two elements, then the product has a meaning. It is another element of the group. And you oblige that the product is associative like the real numbers. Within this set, you have an element called the identity element, which satisfies that the multiplication of any element of X with this element gives the same element. And within this kind of things, you can also invert. This means that whenever you have an element X, so 1 over X exists in the same group. So this is a kind of groups. This is general the definition of group. So for instance, the easiest example is the circle, which is quite a bit different from the kind of the group you know. This is a compact group, and it is all the complex number written down as the exponential minus e theta with theta is a real number. So this is a group. So this satisfies these axioms I mentioned here. And in general, this group manifests themselves through symmetries. They most often appear as a symmetry of object. And in this case, the multiplication is the composition of those symmetries. So just you look at the group of symmetry of one object, and then the multiplication is the composition of all these symmetries, and you obtain something like something which has the property of a group. And a symmetry, by definition, is any transformation which preserves an object. So let me give an example. So if you have, for instance, the rotation of the sphere around an axis with a determinate angle. So you have a rotation of this sphere around this axis, and then you look at another rotation here at this level, and then you look at the composition. So the composition is exactly our multiplication. So this is the multiplication in the group. So the identity element, that is the rotation by the zero angle, something which does nothing. It doesn't rotate the sphere. It is something like that. But in this case, the composition is the same rotation. So this is actually the unit element in this group. And what is the inverse of a rotation? It is a rotation by the angle minus theta. So if you turn the sphere in a given sense, so the same rotation with the opposite sense is exactly the inverse element of rotation, something like that. But in this case, the composition, it gives you something which is stable, which does not act on the sphere itself. And in this case, the set of all rotation of the sphere is a group, as I mentioned. It is noted as O2 of R. And if we allow reflection across subspaces, of course, we get a bigger group noted O2 of R, which I will explain in a better way next. Okay, so this is an introduction to say that the symmetry groups are very important in nature because so these symmetry groups are present everywhere, especially in nature, and then in many sciences, in many specialties, we need to describe some symmetry groups in order to introduce a lot of calculus, a lot of mathematical details. Okay, now a Lie group can be thought as a beautiful structural puzzle composed of two perfectly interlinked pieces. The first group, as I explained, and then smooth manifolds. But why smooth manifolds? Well, so smooth manifolds, it is something, I don't go through details, but manifolds because I need some coordinates. I will give an explicit examples. But if you have a group, an abstract group, it is sometimes, it doesn't have many of good properties, at least, but when you introduced a structure of manifold, this means that you have local coordinates, and these local coordinates are capable to give us the capability to make the calculus, to make integration, derivation, etc. And the structure of a manifold makes the group locally like an Euclidean group. So if you fix a point, so I have some neighborhood on the group on which you can make this operation adjusted, like calculus, integration, and so on. And they are among the most basic and fundamental building blocks of the modern geometry. So by definition, Lie theory is the mathematical study of symmetry groups by their transformations. So it appears whenever such symmetries are found in nature, and it provides a powerful framework for analyzing the behavior of this symmetry. So this is in whole the Lie theory. Now I need to introduce the Lie algebra of Lie group, which is the tangent space at the identity element. So this is very something very easy. Just you have a Lie group, so a group with the structure of manifold, and then you fix the element, the unity element, and then you draw a tangent space, and this is called Lie algebra. I will give some example in order for people who are not very familiar to this theory to understand what is the deepest meanings behind this geometric notion. For instance, in the case of the circle, so the unity element is this point, 1, and then the tangent space is the real line. So the Lie algebra of this circle is just the real line. So in a neighborhood of any point, you can draw a line on which you can make a lot of things, especially integrals, differential forms, calculus, integration, and so on. But this done locally, not in the same, not exactly in the case of the Euclidean group, but just locally. So we can think also about higher dimensional examples, and the meaning is similar. So it simply means that the neighborhood of a given point does not look like a line. For instance, if you look at this form, then this is the two-dimensional manifold, and then when you fix a point on this manifold, then you have a plane as a tangent space. So in this case, the dimension of the Lie algebra have a bigger dimension, which is 2 in this case, And then the idea and the concept behind that is similar. So this is an example, but this is not a real example, but just in order to illustrate the notion of Lie group or Lie algebra to people who are attending this webinar. So if you assume or if you imagine that the terrestrial globe is the Lie group, then the Lie algebra is just a chart. When you fix any point in Africa, in Asia, in any point in the Earth, then you can draw a tangent space which is similar locally to a local space, to Euclidean space, and this is the idea. Why we badly need coordinates? Of course, the illustrative example I gave is the surface of the Earth, and it is natural thing that to impose some coordinates on this. And on Earth, these are, of course, the latitudes and the longitudes. And why I was explaining why we badly need coordinates. And I explained that as an illustrative examples. So the surface of the Earth is the natural thing to impose because we need some coordinates. And the coordinates in this setting are the latitudes and the longitudes. And this is the reason why it is very useful, for instance, in many other settings. And the idea of surface Lie was similar. How to impose on the Lie group some coordinates in order to have the distant tangent space, which is locally the same thing as the Euclidean space. And in this case, we can do a lot of mathematical things. And this extends to a lot of other domains like physics, biology, medicine, and so on and so forth. Okay, so I was explaining, so thus there are a lot of Lie groups in frequent uses. For instance, the higher dimensional sphere, like S1, the rotations in the n-dimensional space. And the fact that we need these things because instead of looking at these matrix groups, so we can consider them simply, we can approach them geometrically instead of looking at them as simply matrices. And they are among the most fundamental family of Lie groups. For instance, I define the SON of R. You can define the same thing, SUN of R. So the Hermitian matrices with determinant equal 1. And also you can define the SLNC or R. So this is of all U such that the determinant equal 1. I will give you some examples in many life sciences how these groups, when we approach them geometrically, can give a lot of applications. Okay, so what is the impact of Lie theory on natural sciences? For instance, if you look at in the case of mathematics, so they are almost perfectly well connected, plenty of applications in harmonic analysis, algebra, geometry, deformations. And this is a list of some important fields where we can apply Lie theory. For instance, algebraic topology, algebraic geometry, combinatorics, differential geometry, number theory, low-dimensional topology, Riemann geometry, and George theory. I will explain a little bit, but I won't go through details because this needs a lot of circumstances to introduce, a lot of material to introduce, but at least I will show some applications. In physics, for instance, Lie theory is ubiquitous also. So you can use that in quantum theory, electromagnetism, particle physics, classical mechanics, and so on. And for instance, it is very important to say that the group U1, it describes phi symmetry, for instance, which is crucial in electromagnetism. SU2 disappears in weak interactions and the theory of angular momentum. SU3 describes the strong force. SO3 governs the rotational symmetries. And SL2C, it is related to the Lorentz group and special relativity. This is some instance. And I put on the screen some reference here. You can go through these references in order to understand how these Lie groups, these are Lie groups, how Lie groups give a lot of potential materials in order to study all these physical things. In chemistry, this is also very important. For instance, SO3 it describes the rotational symmetry of molecules, which is crucial for understanding the rotational spectra. SU2 it is used in describing the spin of electrons, especially in quantum chemistry. U1 describe the phase symmetry group, which is useful in describing aspect of molecular orbitals. And SU2 describes planar rotation symmetries, often applied to the study of planar molecules in vibrational modes. And of course, you have some references behind that. I won't go through how to use this, but the idea is to introduce this group of symmetry locally or globally in order to explain a lot of phenomena within these domains. In biology also, the group SO3 it describes the rotational symmetries, especially in biomechanics and protein folding. SU2 it appears in the spin system and sometimes in biological quantum systems. Through this is more speculative. SON it describes also higher dimensional symmetries, useful in understanding complex biological structure or dynamics in higher dimensions. And Lie algebra. So now I come to Lie algebra in biology. So this describes the local symmetries in biological systems, often applied to understand small deformation or changes in biological structure. And this is very useful, and this is have a lot of application beyond the setting of Lie groups. So for medicine, for instance, SO3 it is used to describe rotational movement, essential in medical imaging, biomechanics, and surgical robotics. SO3 I will define that in 2 moments. This is another Lie group, which is also very important, which represents both rotations and translations used in image registration, robotic surgery, and radiotherapy planning. The Lie algebra, also in this setting, provides tool for understanding local symmetries in biological systems, especially useful in deformable image registration and natural modeling. Of course, if you like to go through all through detail in that, you can of course look at these references, and there are more references to explain all these things. It is more surprising in earth sciences, for instance. If you go through the use of this Lie theory, you can approach seismology and wave propagation, dynamics and geophysical fluids, crystallography and mineralogy, plate tectonic and geomechanics, data assimilation and computation geoscience, and geodesy and gravimetry. So all these things which badly needs the symmetry groups, but not necessarily the kind of group, but now we need to draw some coordinates in order to explain a lot of things, a lot of phenomena related to these domains. Of course, now, if you go through literature, you will directly understand that the groups are not sufficient. So symmetry groups in themselves are not sufficient. We have to go through more complicated things. It is homogeneous spaces. I will explain why homogeneous spaces and how to construct homogeneous spaces and what is the necessity, what is the use of these homogeneous spaces. So for instance, assume that you have a group J, which acts on a space X, and this group can be understood, and it is often best understood through the way it acts or transform other mathematical objects. And the best way to explain the action group on a space, it is the notion of Euclidean motion groups. I will explain in a moment. And in the nature, in many sciences, the action of some group of symmetry groups on spaces are even spaces for which the structure is not very beautiful, but they are very important because it allows to understand at least locally what is the structure of this space X. And a notable example is the permutation of polynomial roots, which Galois led to it in order to understand the profound notion of Galois groups. This captures the symmetries underlying algebraic equation. So in the case of Galois, so there are some finite groups acting on this family of polynomials, and they are very, very useful to produce solutions, how to solve many kind of family of polynomials. And if you think of J as a symmetry group, this means that any point of X can be reached from any other point by symmetry. And in this case, this action is called transitive action. So transitive action means that if you fix 2 points in the space X, there is a kind of mirror between these 2 points, and this mirror can be schematized by the action of this group. I will explain in a moment what is the utility of all these groups. And a transitive equation action of the group defines the geometry, because in this case, the space X in whole is exactly the image of 1 point through the action of the group. So we have only one orbit through the action of this group, which determines the space. So it defines the notion of geometry. And it is called in this case homogeneous spaces. So if you have an action of a group on a such space X, so this builds a geometry, and the space itself is called homogeneous space, and it is in general written down like this, and H is a closed subgroup defining the model geometry of X. So during the whole lecture, for me, a geometry is a given transitive equation of a group on a space, which entails that the set X is written down all the time as a quotient of G mod H, where H is a closed subgroup defining the model geometry. And of course, this is not a group once again, because it can have a complicated structure, but at least it is defined a geometry on X. So let me explain, as I promised, the notion of a Claudine-Mesh group. So Élie Cartan was elected as a foreign member in the Royal Society in 1947, and he published between the two words the following nice paragraph. So he said the following: the elementary geometry is essential in the theory of invariant of certain group, the group of Euclidean motions, and its purposes is to indeed to study the properties of figures that are preserved by an arbitrary motion, stating that all motion form a group which expresses in a precise language the axiom according to which two figures equal to third are equal to each other. I will explain that in a very illustrative way and clear way. So imagine if you have some geometric form like that, and two objects are said to be identical in form if we can map each one onto the other by a motion. For instance, if we can associate some geometric forms into each other, for instance, these two forms, first we can use the parallel translations, like that. So we can translate this form, and then we use the rotation. Now we rotate these forms, and now I can use reflections, and at the end, by using the reflection, I got the same form. So two forms are said to be identical in forms if I find some group actions in order to identify any form to each other, which is quite easy to understand. And in this group, I used the parallel translations, the rotations, and the reflections. For instance, if you have some form like that, by one group action, you get this forms. Now they are reorganized in some way, but in another group action, you can get the word mathematics. So the word mathematics is produced through a group action of some geometric forms, and this group is exactly the occlusion measure group because it includes the rotations, the reflections, and the translations. And of course, this is just an example, but in nature, in many sciences, this has a lot of applications and a lot of circumstances. Okay, so this group is noted like that. So E2, this is O2, the semi-direct product, O2 with R2. And O2 is the rotations and reflections. R2 are the translation. And the occlusion group acts transitively on the Euclidean space E2. So E2 is just the Euclidean space, which is in our language as mathematician R2. And this group acts as a transitive equation. So the action on these forms, like I explained that, this is actually a transitive group when you look at the Euclidean space. And then E2 results geometry, as I explained, because you have a transitive action of such a group. And it is defined by the symmetry determined by the action of E of 2. And this is just an example why we need geometry, because in nature, we have a lot of circumstances when you have some group actions and they act transitively on their space. So homogeneous spaces lie at the heart of my research, just as they did nearly 2 centuries ago for Felix Klein, when he formulated his modern and unifying definition of geometry. And this is the first time in history when we find the correct, let's say, definition of geometry. And the revolutionary Erlangen program proposed by Felix Klein in 1872 classifies geometry through the lens of transformation group. Whenever you have a transformation group, you have on a, this means that it is a group action on a space. You have exactly the notion of geometry and the notion of homogeneous spaces. And homogeneous spaces for a group is equivalent to the notion of geometry, as explained. And in the first time in history, as I said, we have a very precise and deep understanding of what a geometry is. For instance, this can be classified. So it is not a complete classification, but when you look at the setting of Euclidean geometry, you have the action of the Euclidean group, and you can also speak about the affine geometry, the action of the affine group, so the linear transformation plus the translation. You can also speak about the projective geometry. This is the action of the projective group and project transformations. And you can also speak about Riemannian geometry, so the action of local isometry, and so on and so forth. So whenever you have a group action, which is, let's say, transitive, then you create a new kind of geometry. And this is the first time in history where Felix Klein published his Erlangen program when he determined explicitly the necessity to go through this classification and through the notion of geometry. After that, Albert Einstein gave the physical realization of the spirit of Erlangen program by asserting that the law of nature are invariant under general coordinates transformations. And this is very important. So the idea is the same. And in this case, he modeled the space-time as a pseudo-Riemannian manifold whose curvature reflects the distribution of mass energy. So the idea was the same, but in order to interpret it in the general relativity program and in a physical way. And this was very important. And Élie Cartan had something which is very, very philosophical. Nature is not absolutely homogeneous. So the question is, once we have all this description of geometry, can we assert, for instance, that the universe or the nature is homogeneous? And Élie Cartan adds that nature is not absolutely homogeneous. You cannot imagine that in our universe, we can have that our universe is actually a homogeneous space. It's not a geometry, it is not absolutely homogeneous. I will explain that. So the insight of Charles Ersman reflects the realistic complexity of geometric and physical system. So he said explicitly, no absolute homogeneity, but rather local homogeneity. What is local homogeneity? So as I explained in the very beginning of this talk, so the idea is to take a Lie group and then to take any point and then to draw a curve or a line around this point. So the local homogeneity is to do the same thing, but when you look at a point in the system, then you can build a neighborhood of this point which is actually homeomorphic to homogeneous spaces. This is the notion of local homogeneity. We cannot speak about homogeneity. This is very nice thing, but in general, in nature, in many scientific domains, you need to go through this local homogeneity. And this local homogeneity can be explained by the following. For instance, it is determined by a triplet. First, a Lie group, which acts locally, continuously, and transitively on a set X, and then you have a geometry. So X is something like G mod H. So you have a closed subgroup H of G, defining the model of the geometry of X, and you have a discontinuous group. So this is a discrete groups for the homogeneous spaces. And in this case, so let me explain that. So we have here the space X, you have the transitive action of this group. So X is something like homogeneous spaces here. But when you speak about the local geometry, you need to have another discrete subgroup gamma in J, which acts on the space X. And the resulting quotient space, this one, is called Clifford-Klein form. So a Clifford-Klein form is nothing but gamma mod X, which is gamma mod the G mod H, and X is nothing but this geometry. I will give some examples. And when you go up to a higher dimension, instead of looking the Euclidean motion group explained by Élie Cartan, you can look at n-dimensional Euclidean group, which acts transitively on the Euclidean space, En. And this, of course, this action is transitive. And then you end up with the fact that the En defines the geometry of the Euclidean space where we are living now. So everybody is living in some Euclidean space, En with n-dimensional. So n can be the coordinates, the time, the energy, many things. But we are living in some Euclidean space where we have another group, which is the Euclidean group, which is active over there. And more explicitly, so if you look at this case, the discrete subgroup, so this is what I call the discontinuous group is nothing but the integer groups, so Zn. So Zn is this discrete subgroup of En, and as I said, En acts transitively on En, and the resulting is the torus. So now the torus shares with En the same property, but at a local point of view. So so En, the Euclidean space, and Tn are the same things in terms of dimension, but the only difference is that they share the local property, which is the flatness. I will give you an example, a concrete example, in order to understand this mathematical issue, which is actually crucial and very important. So this is the example. So for instance, if you look at the globe, so if you fix, so the globe, when you look at it as a sphere, let's say it is a compact in some sense. So you can assimilate it as an illustrative figure, an illustrative example as the TDN, the torus of n-dimensional. And this actually has the local property of flatness with this chart. So in any point, you have some chart like that, which is exactly the tangent space. And this is explain why we need to define this notion of Clifford-Klein forms. Okay, so I asked artificial intelligence to produce some Clifford claim forms, and the answer is that. So this form actually comes from a transitive action of group, but there you have a discontinuous group. You have this group acting properly and discontinuously, and this gives many let's say figure many interesting things in nature for which we cannot imagine simply by looking at the action of transitive action. So the going forward to the local homogeneity is something which is very important because it allows to construct all these Clifford claim forms and to produce new things. So let me now use all this, exploit all this in order to define the deformation theory and some outcomes. Building on the fundamental notion of group, manifold geometry, and the profound interplay between them, my contributions focus on advancing the deformation theory of Clifford claim forms within the setting of solvable Lie groups and their compact extensions. So this framework offers a concrete approach to tackling the local rigidity conjecture. I will explain that in illustrative way. So for instance, so the Erlangen's program introduced by Felix Klein says that a geometry is a space plus a transitive group action. And now for me, deformation, what is deformation? Deformation is a given geometry. So this means geomodage, and we have a discontinuous group action. So the association of a geometry with a discontinuous group action is actually this defined the formalism, the machinery, the arsenal of deformation. I will explain that in some illustrative examples. So the kind of Lie group I'm looking for, so this is the classification of Lie group in general, abelian, nilpotent, exponential, solvable, reductive, semi-sample, sample. But in my framework, I'm looking at the solvable setting, but this is not sufficient. We remark that many consequences, many aftermath coming from the detailed analysis we did on mathematics needs that we look at the semi-direct product of some reductive groups, semi-simple groups, simple groups on this kind of groups. So this create a kind of complicated groups which are very important in nature, like the group introduced by Élie Carton, the Euclidean motion groups. And in this case, so the local rigidity conjecture I introduced in 2011 says the following. So whenever you have a connected nilpotently group, simply connected also, and you have this gamma, this discrete gamma I was talking about is non-trivial, then any Clifford claim form, so the double coset space, deforms continuously. Unfortunately, this conjecture is still open, but we have solved a lot of restrictive examples, and this is published recently on a book. I will show that. But this still exists. So for people who are not familiar with this notion of deformation, what does it mean exactly? So it means the following. So in other words, so there is an infinite continuous way to deform the discrete subgroup gamma with the assumption that geometric structure of the deformed Clifford claim form are preserved. So imagine that you have a Clifford claim form here, and you have an action of one gamma. So you get this deformation of the structure. So this is a first deformation, but you can have a kind of another deformation, something like that also. And you can have another deformation like that. So the conjecture says that there is an infinite continuous way to deform in the setting of simply connected nilpotently group. And this is very important to understand that within these circumstances, in order to classify all the geometric structure on a Clifford claim form, this is a very difficult task. Of course, when I said there is an infinite discontinuous structure on that, this means up to equivalence. Of course, you can have two deformation which are equivalent. So they have the automorphism group acting on that. In order to, I don't go through details, but at least you have some group for which you can assimilate the same deformation. But what I'm seeing here that you have some independent deformation, so intrinsic deformation, and the number is infinite. And the separate example is this that whenever the group fails to be nilpotent, for instance, the R2, this is the affine group of the real line. So it is not nilpotent group, while it is homeomorphic to R2, but you have a law on this group for which it is not commutative. And then if you fix H, this line, so the real line, and you fix G mod H here, so this axis, and you look at this group Z acting on G mod H, then in this case, you have only two orbits. So the number of deformation in this case are only two deformations up to equivalence, which shows that the conjecture says the necessity of taking the setting of nilpotent. And just nilpotent, imagine that you are talking about the upper triangular matrices with one on the diagonal. So this is the easiest example in order to understand of this nilpotent group. Of course, this is out of the scope, out of these examples, and so on. And so I published the first book in 2022 about explaining all the dynamic of this deformation theory of this continuous group. And then I published a second version of that when I explained exactly the geometry of Clifford claim forms, the local rigidity conjecture, I explained that, and the stability concept. There is a huge geometry problems behind the stability concepts and beyond the local rigidity conjecture. And in these books, of course, I explain this structure theory of solvable groups and their compact extensions, various geometric and topological concepts related to the deformation of moduli spaces, the newest approach and method in deformation theory, the local rigidity conjecture. So I gave some illustrative explanation of that, and also the topological and the geometric notion of stability, Hausdorff and the Calabi-Marcos phenomena. Also, I explained that in the full details in the book of 2025. And if you look at the literature, you can find many applications of deformation theory in life science. For instance, in physics, this is very useful in general theory, general relativity and liquid crystals, in chemistry also for crystallography and molecular reaction, in biology for proteins and biomolecular structures, in medicine, and so on and so forth. So we don't have time in order to explain a lot of things there, but at least we can figure out that the number of lubrication using this deformation theory is very important and huge. So let me finish this talk by explaining how these geometrical facts, how the representation theory built on these symmetric groups have very important application. For instance, in the setting of Rn, so the notion of the Fourier transform is very important. So the Fourier transform is given by just you look at some integral function and you define this integral. So just you multiply the function by this unitary character and integrate against the Lebesgue measure, and you get the Fourier transform of a function f. When you go through the generally group, so in general you don't have characters for the simplicity case. So in this case,
Ali, I think we probably have 5 minutes to go according to the watch.
So I should finish in 5 minutes?
I think it's that's my understanding, right, Sirafiq?
Okay. So Sirafiq, I think told me that you can go till 1 hour, but I will finish if you like.
Okay.
So just to explain, it is very important to define the non-commutative Fourier transform, which has many applications. Maybe today I don't have much time to explain what are the uses of the non-commutative Fourier transform. But imagine that you have a group J acting on the Lie algebra, but this is the vector space of the Lie algebra, and then this produces some orbits, quadrant orbits. So in nature, the quadrant orbits are, if you want, you can draw this orbit like this. So they are smooth manifolds behaving like that by layers. And the idea is when you consider this integral, you have to figure out what is this pi of g. So this pi of g is a representation, and this representation in physics, it is the abstract mathematical way to express it as a transformation of vector basically by matrices. So just it is an action, but in this case, it could be infinite. And when it is infinite, we don't speak about matrix, but at least we consider this as an action of a group, and this define unitary representation, reducible representations, and then this associated to our orbit. And then there is behind a deep, geometry that. And the problem is to identify what is the relationship between quadrant orbit and the unitary representation. So there are a lot of theory, for instance, developed by Roger Howe in the States, Pedersen also, and Wilberger. And I have pleasure to introduce this conjecture. And this says what I'm doing since a long time with Dominique Manchon from Clermont-Ferrand, how to characterize, how to get a quadrant orbit, an object related to this representation with which we use the non-commutative Fourier transform. And we have written this book with Hidenori Fujiwara from Fukuoka, Japan, and with John Ludwig from MES. And this explains the representation theory of solvable groups and what are the consequences of looking at the non-commutative Fourier transform harmonic analysis in this setting. I end this talk by saying that the problem the problems we solved recently, so this represents some deep problems in representation theory and in geometry, which has their profound applications in life sciences. But I have to confess that even myself, I don't know exactly what are the applications. But for instance, this problem of the closedness of product of Pukansky project is very important problem. So this says very roughly that within this integral, we define the Fourier non-commutative Fourier transform. You have to modulate when you have two representations, how to modelize, how to write an operator which renders this Fourier transform more readable. And recently, so we solved completely different polynomial conjecture, which has deep impact on the resolution of differential equations and partial differential equations. And also some problem related to Benson-Radcliffe conjecture, Corwin-Griffith conjecture, and also two parallel questions for restrictions, and also this conjecture which is not completely solved, at least in the exponential setting. So we have a forthcoming paper, but a second is in progress. And finally, I would like to say that so the local rigidity conjecture I explained is still open, and I hope that we find some new idea in order to have some solution to this kind of problems. So let me thank you very much for your patience and for this kind invitation once again. Thank you.
Okay, thank you very much, Ali, for this beautiful talk. Very instructive. The floor is open to questions, please. If you have any questions to Ali.
Yes, possibly I have one question. So I am not from this field, so it will be a very naive questions. But when you talk about the pi, the representation pi, when you were doing the equivalent of the Fourier transform, you said that, oh, it's no more a matrix. So is it an operator, and is it an operator in some Hilbert space, countable
Exactly,
basis? So,
exactly.
so you could in fact still see it as a matrix with a countable size.
Exactly. So this is an operator. A unitary representation is a pair pi h, where h is the Hilbert space, and you have an operator pi from G to the group homomorphism in the unity of operator of h.
Ah, yes,
And
okay, it was here. Okay.
yeah, this modelize exactly the how to replace the simple unity character here with the representation. Is of course this could be infinite. In general, for instance, in the solvable setting, in general, this is an infinite dimension. So this is
Mhm.
you can look it as some infinite matrices.
Okay, and quite often for those operators, you have a lot of functional analysis questions. So, for
Exactly.
example, is it the case that if they are compact, you have something special in your field, or compactness is not playing any role in general here?
Compact is very important and very active things. But in this case setting, in the active setting, all irreducible unit representations are of finite dimensional. So the compact case is a very special case. In this case, so H is a finite dimensional vector space. Okay, and this representation is of finite. So you have here a finite dimension matrix. Okay, so this is in some sense the easiest case. But in my
Mhm.
case, in the setting of solvable Lie groups or the compact extension of solvable group, this is never the case. But in the compact setting, things are simpler.
And what represents here in this integral dg? The integral is
Did you hear the hard measure of the group? So in this kind of group, we show that there exists a unique measure on the group, which is left invariant up to constant. This is called
okay.
the hard measure on any locally compact group, not necessarily the group, but on any locally compact group, you have the hard measure, which is a G invariant measure, and it is unique. Left invariant measure, it is unique up to constant.
Okay, and this integral is, in some sense, is finite for
Of
all
course,
pi. Okay,
of course. If you look at some function which is integrable, f1,
okay.
so this operator is unitary, and absolutely this integral converges.
Okay,
Because the norm here, you can so you can dominate this integral by
fg.
the norm of the function the norm one of the function f. Of
Okay,
course, this is all the time convergent.
okay.
And behind you have the Plancherot formula also.
Okay.
I have possibly another questions. At some
Yes,
time, you mentioned a lot of keywords for the Lie group, enfin, solvable, simple, and so on.
yes, yes.
Uh, so is it the case that it is always the case that the terminology is in fact applied to the group to which this Lie group is associated or Lie algebra is associated?
Yeah, of
So,
course.
so yes, you had this.
Yes, this. Yeah.
Okay, okay. So it was not Lie algebra, yeah, it was Lie groups. Okay, okay.
No, no, only group. Yes. Yes. So the
Mm.
the compact groups are on this side. Huh?
Mm-hmm.
In this side, there is no compact group, at least trivial.
Okay.
What I mentioned is that sometimes we need to look at the action of a compact group on a solvable or exponential on a potential group, and this create another dynamics, which so for the representation it's more complicated, and but sometimes we need to middle with that in order to solve deep problems and so on. We need like exactly the setting of Elie Cartan. Elie Cartan associated the R2, which is a abelian group, with the group of rotation. So the whole group, so the semi-direct product of O2 with R2 is not a commutative group, But in nature, in physics, it is very important. And as we saw, if you go through many other specialties, many other domains, you can find a lot of application using these groups.
Okay, and at the end you had a set of conjectures for people who are not expert in the field. I don't expect to solve any of these conjecture, but which one you would advise to have a look on because it is perhaps easier to understand or funny to play with, perhaps with computer algebra or whatever.
Yeah, this is a very nice question. So as I said, so beyond the theoretical framework, lie profound open problems which deeply rely on these conjectures. And I confess that I'm not very specialist in applications. For instance, so this Corbin Greenleaf conjecture, this one, it says that the algebra of differential operator on this homogeneous space, G mod H, I explained in the very beginning of the talk. So the algebra of differential operators on this space with some condition which is called finite multiplicity condition is exactly a polynomial algebra. But this is very important. So I wrote another paper which says that in this setting, in this non-commutative setting, any differential operator on these homogeneous spaces can have fundamental summutations. So this means that you have some distribution, E, for which the convolution product is the direct measure. And this, of course, solves a huge kind of differential problems, of differential operator problems. And the Zariski closure conjecture is very important because so far, we don't have any means in order to associate in the level of the Fourier transform this operator P, this representation P to a geometric object. So the conjecture I posed with Dominique Monchamp from Clermont-Ferrand says clearly that in the setting of exponential solvable group here, in this setting here, we get a nice picture how to represent these representations, which is within the integral with a geometrical object. And this is very important. So the non-commutative Fourier transform comes to be written down using geometric objects. So mathematically speaking, it is written by an infinite dimensional operator, but in real things, it is defined by geometric objects.
Okay, thank you for these questions. Anybody has other questions?
Yes, please. Yeah, I have a question.
Yes, please. Who is that? Absatar?
Yes.
Yes.
Yes, please go ahead, please.
Thank you very much, Prof. Ali, for this nice presentation. And I'm really happy to reach your talk. Indeed, for the Fourier transform,
yes,
and with that issue of infinite size matrix, is it possible to consider instead the representation of the group valued in sister algebra?
This is another problem. Yes, of course. So you mean sister group algebras or general algebras?
Yes, to solve the problem of infinite matrix, we can embed into a sister algebra, and then we have everything complexity.
Of course. So I won't go through the theory of sister algebras, but in general, the sister group algebra. So they are something like you take any locally compact group, J. You look at L1 of J as a set with respect to the R measure. I explained this measure, and then you have an involution there, and you have a norm there, the norm of sister algebra, and you get this as a sister algebra. And of course, you have more means within a sister group algebra, and you have the same definition. I mean, you can define the same Fourier transform on this sister group algebras. And Hedir Jaiba, who is my students present in this here, is a specialist in that. We introduced the Fourier transform on sister group algebra in order to give a characterization of this sister group algebra which is a very complicated problem, using the Fourier transform. So it
I
is
see.
very useful. Thank you for the question.
That's very interesting. Indeed, there is quite interesting problem, which is close to representation theory. Concerning the what's called the Ogata index of SPT order in many-body physics. Indeed, Ogata is a Japanese mathematician who showed that starting from an topologically problem of in the physical system of spin, she showed that to characterize these classes, she get the invariant is topological. Is the second group cohomology. I think going into this direction is also quite interesting and fruitful.
Okay. This is another direction, but I'm not working on cohomology group. But I'm confident that in order to solve the local rigidity conjecture I introduced in the Japanese Academy, we need to go through cohomology. Yeah, I agree. Yeah. Okay. Thank you. Yeah. Thank you.
Thank you very much.
Okay. Thank you very much for these questions. Any other questions?
Yes, please. Thank you, Professor Ali, for this nice talk. Could you think that there is a natural probabilistic interpretation of deformation of Lie groups? In particular, can you think of a deformation as a stochastic perturbation of the symmetry structure where the group Lie, the Lie algebra, or the representation is subjected to a random fluctuation?
Yeah, we can conceive that, but I have to confess that I never looked at this probabilistic point of view. But there is a lot of specialists worldwide working on Lie group theory with respect to this probabilistic approach. I never approached that, but I guess that there are some people working on that. In terms of deformation theory, I'm not quite sure. But at least in the group theory, there is a lot of people working, so approaching them as some in a probabilistic way, let's say. For instance, I gave a talk recently in Oxford, where I mentioned that the one of the consequences of defining the non-commutative Fourier transform is to introduce this Levy process on non-commutative structures. Because when you introduce the Laplace transform on some Lie group, it is in itself very, very important questions and deep problems. But so far, we cannot, we don't have any idea about this problem. So I constructed that in a very precise way for nilpotent Lie groups. And in this case, we approached a little bit the probabilistic way in the Levy process in the non-commutative sites. Yeah, but for the deformation theory, I never thought about that, and I even didn't see any people working on that. I don't know. Maybe there exist.
Okay. My last general question. Could you provide a concrete example of application in medicine or in physics, for example?
Of course, the application I gave, so this is very rough, but I developed all this application in some other talks. For instance, in a talk given at the Faculty of Science of Tunis by one association there, where I explained exactly the necessity to go through these symmetry groups in order to interpret a lot of medical things. And also in other talks by the Tunisian Society of Physics, by Samia Sharfi, Professor Samia Sharfi invited me to present, let's say not the application, but some applications of this conjecture to this. I developed some applications, but it is, as I said, I'm not specialist in that. But if you go through literature, you can find a lot of the documentation there.
Okay, thank you.
Okay, thank you very much. Okay, more questions. Okay, great. I thank again Ali for his talk. And I'd like to give the floor to Professor Rafiq to close this session today.
Thank you again, Professor Ali, for this nice talk, and thank you, Professor Sadek, for your presentation. And see you next week with another talk. Thank you very much.
Thank you very much. Yeah, thank you for the invitation.